Steam turbines operate by integrating thermal cycles, including the Rankine cycle, reheat cycle, and regenerative cycle. Let's understand a little more about this. In short, the objective of any heat engine is to transform heat into work. To do this, throughout the thermal plant we use some type of fluid of work that goes through the thermodynamic cycle. The cycle of a steam turbine consists of receiving high-grade steam, pressure and temperature generated by a boiler, and convert the thermal energy of this pressurized steam into mechanical work through the expansion of steam in the rotor blades, which in turn activates some mechanical or power generation equipment itself, the electrical generator. Later, as we will see in detail later, the steam may still contain energy to be used in other processes. Case of counterpressure turbines, or it may no longer have energy to be converted and reused, as in the case of condensing turbines. In the latter case, the steam returns through the turbine exhaust to the condenser, where it is condensed. Roughly speaking, he is turned into water and pumped into the boiler again, thus restarting the cycle. This cycle is already well studied and was named the Rankine cycle. Name of its creator: Scottish engineer and physicist William Rankine. Briefly, the cycle comprises receiving heat from a hot source, perform mechanical work during the expansion process, reject part of the heat received and not transformed into work to a cold source, and consume part of the work produced in the expansion to return to the initial stage, thus completing the cycle. Briefly, the Rankine cycle is a thermodynamic cycle that converts heat into work. The heat comes from a source external to the closed circuit of the cycle, which normally uses water as the working fluid. As I already mentioned, this type of cycle is responsible for approximately 80% of all electrical energy generation in the world, including thermal, biomass, coal and nuclear plants. The Rankine cycle describes the operating model of steam engines most found in power generation plants. The most commonly used heat sources are coal, natural gas, biomass, oil and nuclear fission, which is not very common here. The efficiency of the Rankine cycle is limited by the working fluid. The working steam temperature range for the cycle is narrow, which can reach around 600 degrees Celsius at the turbine inlet. This is already the normal limit for many materials, and around 30 to 50 degrees there for the condenser. This results in a Carnot efficiency of approximately 63%, with the real efficiency of a typical plant being around 42%. The Carnot cycle and the Rankine cycle are two cycles. Much discussed thermodynamics related to heat engines. The Carnot cycle is a theoretical cycle that gives to the machine efficiency that can be obtained by a motor in a theoretical way. The Rankine cycle, on the other hand, is a practical cycle, which can be used to calculate real-life engines. So what is the difference between the two Carnot and Rankine cycles? The Carnot cycle is a theoretical cycle, while the Rankine cycle, it is a practical cycle. The Carnot cycle, it guarantees maximum efficiency under ideal conditions, but the Rankine cycle guarantees real-world practical operation and conditions. The efficiency obtained by the Rankine cycle will always be lower than that of the Carnot cycle. Compared to gas turbines, the low inlet temperature of the steam turbine causes the Rankine cycle can also be used as a secondary cycle in combined cycle thermal plants with gas turbines. In this case, the working fluid in the Rankine cycle, we are talking about steam. It follows a closed circuit and is constantly reused. Water vapor, which is normally seen leaving thermal plants into the atmosphere, it is actually generated by the cooling system and not by the closed steam circuit. This represents the loss of heat that cannot be converted into work. One of the great advantages of this cycle is the small energy required during the compression phase, as the fluid is in its liquid phase. At this stage, condensing the fluid before pumping again. For the boiler, the energy required to drive the pump would be, for example, a fraction of 1 to 3% of the turbine's potential, which considerably increases the efficiency of the cycle. This benefit, however, is partially lost due to the low turbine inlet temperature compared to other cycles. As a comparison, the inlet temperatures in gas turbines are close of 1500 degrees Celsius against the 600 degrees and average of steam turbines. However, the shortcomings of gas and steam cycles are quite similar.